I already provided an overview of line codes. In this video, we'll get into the details, but first, a quick recap. An example is this non-return to zero encoding where we represent 0 by a low voltage level and 1 by a high voltage level. Well, you could flip the voltage levels as well. That is, you could represent 0 by a high voltage level and 1 by a low voltage level. It really doesn't matter, as long as you employ a consistent encoding policy. Now suppose you send this particular waveform over a physical media. For now, let's assume that the link bandwidth is sufficiently high that there is no distortion resulting from limitations in the bandwidth. Now the receiver is going to receive a waveform. The question is, how does the receiver decode the bits from the particular waveform of this type? Think carefully. You need to do two things to recover the bits from the waveform. Now, if you had thought that if you received a voltage level plus A, I will decode it as a 1. If I received a voltage level minus A, I'm going to decode it as a 0. Now, this is not a good idea because there is attenuation and noise as part of the media. You may transmit A volts, but what is received at the receiver will not be A voltage. It will be much lesser than A. Okay, fine. How about comparing with a threshold? In this case, this is your decision process. Suppose I view this as 0. Any voltage that is above 0, I am going to interpret it as a 1. Any voltage that is below 0, I am going to interpret as a 0. That is bit 0. This can work great, except that the media sometimes has these capacitance effects. Ignoring any other distortions resulting from noise or limitations in the link bandwidth, if this were the waveform that was sent, if the media has capacitance effects, this is the waveform that you're going to receive. If you have done electronics, you would have heard about this RC constants, which is basically a time constant, which is a product of the resistance and capacitance. These tend to discharge in this particular fashion. Even if you don't understand this, let's work with the assumption that this is the received signal caused due to some capacitance effects of the media. See what's happening here. You actually sent a 1 here, but you are actually getting a negative voltage level. But then the 0 itself is much lower than the minus A that you have sent. So often what is done is the receiver is going to maintain an average of the signal that it is going to see, and it will compare the future received bits with the current average. That way it is able to distinguish between the low and high signals based on the current average. Now this helps to some extent, but this alone will not suffice. That is, comparison with the threshold alone is not enough. Now if you did this comparison, you would have gotten back a waveform of this form. Forget about the bits that are here, just look at the waveform. This is the waveform that you have got. Now look at here. How do you know that indeed this is 3 ones and not 5 ones or 8 ones? So for this, you need to know the duration of a bit, which means you need a clock. Ideally, the receiver's clock should be perfectly synchronized with the sender, otherwise you're going to make errors. Suppose if your receiver clock is running twice as fast as the sender clock, then you're going to interpret these 3 ones as 6 ones because you're going to sample at twice the rate. Even a slight skew in the receiver clock and the sender clock can slowly creep in errors. So you do need a clock at the receiver, and you want this clock to be perfectly synchronized with the sender. Now how do you derive this clock? So one method is to use one pair of wires to send the signal and another pair of wires to send the clock. But unfortunately, this is going to increase the cost of the wire. So most solutions tend to avoid this, and they try to recover the clock from the received signal itself. So how is that possible? Basically via transitions in the received signal. So look at this figure. So whenever there is a transition in the signal, for example, you are going from low to high voltage, you know that this is a clock boundary. So again, this is a transition, this is another clock boundary. Transition, another clock boundary. So based on these transitions, you can recover the clock. So I have summarized here the two techniques we are using to recover the bits. One is a threshold based detection to determine whether it's a 0 or a 1. Another is the transitions. Basically, you need to have transitions to recover the clock. These are the two techniques that you need to recover back the bits from the waveform. Now look at this NRZ signal, stare as much as you want, and tell me what can be the potential problem with this type of encoding, NRZ encoding. If you have consecutive ones or consecutive zeros, the problem is when you're calculating the average tends to change. When you have a consecutive sequence of ones, the average tends to be high. When you have a consecutive series of zeros, the average tends to be low. This can potentially lead to errors. So this phenomena is called baseline wander. Not only this, also the lesser number of transitions. When you have consecutive ones, basically you have no transitions in the received waveform. This can lead to clock drift between the sender and the receiver, which can also lead to error. So a lot of line coding techniques try to provide enough transitions in the signal. Definitely that there should be a transition after a fixed number of bits. So this is what is their goal. So let's look at other encoding schemes that try to overcome these two specific problems. NRZI, which stands for non-return to zero inverted, uses a form of differential encoding. So to encode a 1, you basically make a transition. To encode a 0, you stay at the current level. So I'll show you what I mean by that. So basically this is used in USB. So here is non-return to zero inverted. So whenever you are encoding a 0, you stay at the same level, but whenever you encode a 1, you are going to make a transition. So 1 again, so you're making another transition, 1 again, another transition, 0, you stay at the same level. One very nice thing about this differential encoding is that the actual voltage levels don't matter anymore. So all that matters is the transition from one voltage level to the other, thereby noise cannot have that much of an effect on this type of encoding. So look at this NRZI encoding some more and answer the following questions. So NRZI has some advantages. As I mentioned before, it works well in presence of noise because you are not dealing anymore with the comparison. In other words, there is no voltage levels involved. It's only the transition that matters, and detecting transitions is easier than comparison with a threshold. And now this totally eliminates baseline wander because there is no comparison with any threshold. So you're not calculating averages. And it also helps if you accidentally invert the leads from the device to your twisted pair, because whether you connect the positive to negative or the negative to positive, it has no effect because, again, as I said, voltage levels have no meaning. The problem with NRZI inverted is while it solves the problem of consecutive ones, consecutive zeros are still a problem. So you can't recover the signal in presence of consecutive zeros, and still you have a DC component present. So NRZI, while it is used in USB, is typically not used in Ethernet and other technologies. So another encoding called Manchester basically transmits an XOR of the NRZ encoded data with the clock. Basically this boils down to 0 being encoded as a low to high transition and 1 as a high to low transition. And this is the encoding that is used in 10 megabits per second Ethernet. So again, let's see how this looks. So here is Manchester encoding. So the zeros are transmitted as low to high transitions and ones are transmitted as high to low transitions. So another one, high to low transition, another one, high to low transition, 0, low to high transition. Now, do you think this solves baseline wander as well as clock recovery? Now again, look at this waveform carefully and tell me what can be the potential problem with Manchester encoding. So you're right that Manchester encoding eliminates baseline wander. Since you are transitioning for every bit, it's very easy to synchronize. In fact, it's self-clocking. And there is no DC component because you are moving from low voltage to high voltage in every bit. So it averages out to 0. The main problem with Manchester encoding is it's only 50% efficient. Suppose you were to send this particular bit sequence. In NRZ, if you are occupying a bandwidth B, in Manchester, how much bandwidth do you think it will occupy? Because you have twice as many transitions, you will occupy a bandwidth 2B. So this is the worst case scenario, but in general, because the number of transitions are more in Manchester, you tend to occupy more bandwidth. Even if you are not concerned with the bandwidth, it basically means that if you could use, in other words, you have a receiver that is able to detect transitions as fast as twice your data rate, you might as well send twice the data rate using NRZ or NRZI. That is, one could send twice as many bits in the same time period with NRZ or NRZI, thereby you're only 50% efficient. So Manchester is used in Ethernet because if it's convenience and it provides enough bandwidth that you don't have to worry too much about it. But in some of the higher speed Ethernet, that is the 100 megabits per second Ethernet, this is no more used. Something else is used. So the encoding scheme that is used there is called 4B5B encoding. So in this case, you take 4 bits of the data and convert it into 5 bits. So if you see this table, you will see a certain pattern that these 5-bit code words follow. One is that there are no more than one leading 0. In other words, they always have only one 0 at the beginning. There won't be 2 zeros. And there are no more than 2 trailing zeros. In other words, you won't see 3 trailing zeros. What this means is when you put 2 5-bit code words together, how many zeros, maximum number of zeros, do you think you're going to see? Since that number is only 3, it solves the consecutive 0 problems. And the 5-bit code words are sent using NRZI, which solves the consecutive 1 problem. So basically, you ensure that there is a transition after at least 3 zeros. This scheme achieves 80% efficiency because you are inserting one dummy bit for every 4 bits. In other words, only 4 out of the 5 bits that are being sent are useful, which translates to 80%. So here is a summary of the different encoding schemes we have covered. Encoding basically converts bits to voltage levels or power levels in case of fiber optics. The goal of many encoding techniques is to provide enough transitions for clock recovery, and you want to do this while minimizing bandwidth. And we looked at a variety of schemes: non-return to 0, non-return to 0 inverted, Manchester, 4B5B. Each scheme has certain advantages as well as disadvantages.